like to introduce Victor Olaya from Boundless. Yes,
that's it.
You're working. And then I think you should make your own introduction.
Okay.
Yeah, I just give you an introduction.
Well, I work at Boundless, that's true. We're a company, I don't know if you know the company, it's an American company based in New York. But I work from France, I live in France and I work remotely. And most of my job right now, it's related to QGIS. So I do QGIS development, but it's not QGIS development that actually you're going to find in the core QGIS. And the reason why I'm here is not because I work at Boundless, although we do QGIS stuff, but because I was the author of this processing framework. So this is the framework that is incorporated into QGIS for doing all kind of spatial analysis. I was the main author and I'm the maintainer of that plugin. That is actually a core plugin. That means that when you download your QGIS, it's already included in QGIS. And what we are going to see in these 2 days is basically processing, basically trying to understand the analysis framework and try to do some analysis, try to work with spatial data, etc. We're going to start with some theory about it, but then we'll go to practice and we're going to work directly with QGIS. That I think that is a software that you more or less know a little bit. So what we're going to do is more analysis, and maybe at the end of the 2 days, we're going to try to join that with the things that you saw with Martin, because you've been working with LiDAR data and with LAS tools, but LAS tools can also be used from QGIS through the processing framework. So that's what we are going to do maybe at the end, try to link both things together so you are able to do your LiDAR work from QGIS through processing. So we'll see if we manage to do that, we'll see if we have time, and that's it. I hope you like that. I have a very flexible plan. So my idea is to do some basic lessons at the beginning, like the main ideas of processing, main ideas about spatial analysis, and then whether we can continue with some different kinds of analysis. Lean proposed doing some hydrology, which is something that might be useful for some of you. I think one of the most interesting parts of the processing framework is that you can actually do your own algorithms, your own processes. That needs knowing a little bit of programming, particularly a little bit of Python programming. So I don't know if you're familiar with Python or you've done some programming. So my idea is to start with some very simple scripts. If no one understands that and that's too difficult, I will just switch to other different things. So I'm trying to adapt what I'm going to do to your knowledge, right? Also, there are, like you're going to see, there are many different algorithms for doing analysis. We don't have time to see them all. We're just going to see a few of them. But if there's any area of analysis that you really like or you work in, feel free to tell me, right? So basically, what are you going to see in this first presentation? Okay, I'm going to introduce a processing library, right? It's very simple. You're going to see that the ideas are very simple. Then it's very powerful because it contains a lot of algorithms and it makes things very easy. But the main ideas you're going to see that is really basic and you're going to learn them pretty quickly, right? That's what we're going to do most of the time, not only in this presentation, but during the course, just working with processing. But then what I'm going to discuss now is some common problems that people have in spatial data analysis. This comes from my experience, like processing has been around for almost a couple of years right now. But processing is like let's say the second version of an analysis framework that I developed called Sextante that I started developing almost 9 years ago. So that means that I've been 9 years doing basically the same thing, developing this analysis framework and doing workshops and talking to people, answering questions in mailing lists, IRC, forums, etc. And one thing that I've seen is that most of the people asking things, they can get a very good knowledge of the software itself, but there's still things that they don't know. There's still things that, they're not good users. They learn how to click on the buttons, do things, but they don't understand what they're doing, they have problems. And I have identified 3 main problems of people. 3 main problems that I think if we just solve these problems, I would have better users for my software, right? So that's why before starting with the software, I'm going to tell you about these 3 problems and let's see if we can fix them, right? So what is processing? It's a library, right? A library that is used by QGIS It has two main parts. One is this foundation classes and geoalgorithms, that's like the inner part, right? The processing, where the processing takes place. So that's more like a low-level thing, the more thing more for programmers, right? Foundation classes and geoalgorithms. And then there are graphical elements that you can use to use those algorithms, right? And we are going to see that the same algorithm, let's say an algorithm that takes a digital elevation model and calculates a slope layer, okay, that's the algorithm, very simple thing. We can use it in many different contexts. We can just call it once, and we will use one element called a toolbox. We just call the algorithm, here's my DM, and it produces one slope layer. But we can use it in another thing called the batch processing interface, which allow me to process, instead of one, like 100 or 1,000 different layers at once. I can use it in the graphical modeler, which allow me to define a workflow. So there are different elements that then allow me to take the most out of all those algorithms, right? And this is what we're going to see, right? We're going to deal with a couple of algorithms, but my main aim is to teach you these graphical components so you learn how all the pieces work together. There are two versions currently available. The old one is the old one that I told you is called Sextante, okay? I don't maintain it anymore. There's some people maintaining it. There's one rather well-known version for software called QGIS, but it's mostly maintained by a team in Germany. I don't maintain that anymore. And then it's a Python version for QGIS. This is the one that I currently maintain, right? It's the newer one. It has the same ideas, but completely different implementation. So it's brand new compared with the other. And this is the one that we are going to see, the Python version for QGIS, right? So this is the elements that I told you. We have this toolbox, which is like the set of all the algorithms. The graphical modeler that allows us to define workflow graphically. So this algorithm, and then goes this other one, and you define a full workflow. Batch processing interface to process a batch of layers. And then we have the console, which allows you to call processing algorithms writing code, right? In particular, writing Python code. And this is that part that I told you that I'm probably going to do at the end. We're going to do a little bit of Python code, a little bit of work with that, right? So what is the approach? This is like the new approach from the Java version to this Python version, so you get the idea of it. But processing is a consumer of geoprocessing algorithms. That means that we have all this set of geoalgorithms, right, that I told you, things that are implemented in processing itself. But also, processing takes algorithms from different places. One very good example is LASS tools, right? Martin developed LASS tools. Those are tools that you can use to do your lighter stuff, right? But it would be great to have it in QGIS, okay? Which is the best way of linking a tool like LASS tools with QGIS? The best way is using processing. Because you can put an algorithm that actually wraps one of the tools that Martin developed, and then you can use that in the modeler, in the batch processing interface, in the toolbox, and that's the idea. So processing should be like the entry point for anything that has to be with analysis. That's the philosophy of the tool, right? So it's a centralizing tool. It's something that, everything that has to be with analysis, even some things that are already in QGIS, like Lynn mentioned this vector menu that has disappeared from your software, but there's no problem because all those vector analysis tools, they're already in processing. And it's much better because instead of just having the tool, you have the tool in all those different elements, the batch processing interface, the modeler, etc. It's easier, it's more stable, etc., right? So this is the approach that we use for the QGIS version. It's just a centralizing tool for everything that has to do with analysis. So in short, like the rule of thumb for that is if you're going to go to QGIS and you need some analysis, you should go to processing. That's basically a philosophy, right? Okay, we're going to see more about processing. So we're going to work with it for 2 days. So what I'm going to teach you now is, I'm going to discuss a little bit all these common problems that people have in spatial analysis, problems that most likely you have now. Like if you're going to do something, you want to do some spatial analysis, probably you're going to go to this problem. The first problem is not knowing what to use, or even if there's something that I can use to solve my problem. You have a problem, like I have this data and I want to get to this place, right? You want to solve some spatial problem, and you actually don't know what to use. If we see in the list of algorithms in the processing toolbox, there are around 500 different algorithms. That's a lot. I mean, you get lost, a list of 500 algorithms, right? So you can say, which one do I use? you don't know, even if there's one that you can use. Sometimes there's no one that you can use, you have to program yourself. Sometimes there are 5 different ones that you can use, or 10 different ways of getting to the same result, right? So that's, people get lost in this. And how do we solve that? Well, you need some knowledge, so you're able to more or less find your way in this list of algorithms and find the one that actually you need. That's one of the problems, right? The second one, in my opinion, the biggest and most important algorithm is using things without actually understanding what you do, right? And this is a very typical software problem, sorry. Why? Because, well, you might take that list of 500 algorithms and then you find the one that, you know, it says, this looks like the one that I need, right? And then you execute it. It takes some parameters, you put your parameters, you put your data, it generates the data output, and as soon as you have some data output, you think it's correct. And that's not true. Right? If you don't understand what you're doing, you might be doing something wrong. So that's a really big problem. People thinking that just because they know how to click, click, click and get to the result, they're going to get a good result. And that's not true, right? I answer a lot of questions on mailing lists. People are saying like, hey, how do I use that? And I'm not very popular for that. I'm still popular because I'm the author of processing, but I don't get very popular when I say like, you're not ready to use that. Read a book, then you come back. And people are like, no, no, and then there's someone who says, you do this, this, and oh, thank you. And they do it, and it's like, no, that's not the way of doing things, you know? If you don't understand what you're doing, you shouldn't do it, right? You need to understand the science that is under that, okay, even if the software is easy to use, right? We're going to see some examples. I don't know if you're familiar with interpolation. You have sometimes done interpolation. There's a technique called kriging, which is my favorite and most hated technique, because everyone says like, kriging is super cool. And it's like, how do you do that? And it's like, you cannot use that. You need a lot of foundation and a lot of knowledge. But you know, people end up doing that. And 90% of people that use kriging, they're actually not prepared to use it. And the result they get, they look nice, but they're absolutely useless, right? And the third one is people don't know how to present what they do. Like when you take something like processing, you calculate something, you end up with something. A number, a map, whatever. You have something that is your result and you don't keep it to yourself. You have to, you know, put it in a document or show it to your boss or give it to another scientist that is going to do some other analysis. And usually we do a poor presentation of results and we lose a lot of information on that way, right? So we're not taking the most out of the result, even if the result is correct. Even if you went correctly through the 2 first steps, then you're not going to pass it correctly to someone else. So it's important to correctly present your results, right? So I'm gonna go a little bit more in detail with that and see if you're prepared or not. So the first thing we have to work on, and let's see if you have been working on that, is the spatial reasoning. Okay, spatial reasoning, what I understand by spatial reasoning is the ability of learning how to solve spatial problems. Like, let's put it this way. Imagine like you're at school, right? And you learn how to multiply. Yeah? When you're a kid, you learn how to multiply. Perfect. You learn your tables, etc. Then you learn how to sum and make a difference, you know, basic operation, right? So you know the tools, actually. You know how to multiply, you know how to sum, etc. And then someone comes and puts you this typical problem, like, I have this age and my cousin has twice my age. This kind of simple problem that you do a small equation and you solve it just by using multiplication and sum. But if you don't know how to write the equation, you're not going to be able to solve the problem. Right? So if there's like, I make a very small problem, like you're here 20 people in here, each one is paying 50 euros for this course. How much money do I make? If you don't know how to make the equation, even if you know how to multiply, you're not going to solve the problem, right? So one of the things that people tend to do, and when they work with a tool like processing, is learn the tools, isolate it. They just go, click, 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 and then there's a problem like, here I have 7 layers. The problem is, find me the best place to set my nuclear plant. And then they just do crazy things, like, you have the tools, you know them. It's easy, 1, 2, 3, and it's done. But they try to do other crazy things. Why? Because they don't have this kind of spatial reasoning, right? So the idea is that put the problem and try to solve the problem, right? And that's one way of learning that. It must be developed. It's not something that you know. I mean, there are techniques. Like, you have to, you know, face some problems, get your software, and work. And this is hopefully what we're going to do we're going to do this 2 days, trying to put you some problems and see if you can solve them. That's how I'm going to do it. I'm going to teach you like small tools, small steps, and then just give you some data. And it's like, I give you 15 minutes or half an hour, and then you just work on that. And some of you might be smart and maybe able to solve them. Some of you maybe not, but you know, that's the way to do it, right? The idea is to state a problem and find a solution, the same as what you do with things that are not special. That's the idea about solving a problem. Using the tools that you know, using that sum, multiplication, whatever, okay? So the same techniques, the same idea, the same approach that you use for non-special apply here, right? So that's basically the spatial reasoning. That's the key, to be able to, you know, find the workflow to go from your input data to the output that you want. So it's spatial data. Okay, so how many people here have been working with spatial data for a long time? I guess most of you have been working with spatial data for some time, okay? Probably you've heard this all the time, like spatial is a special, all this thing, right? You know, there's some basic characteristics of spatial data that you have to know, right? If you don't know them, you're just working with something that you don't understand. We're just working with a particular type of data, spatial data, that you actually don't get the full meaning of it, right? How many of those things, who in here knows all these four things? Raise your hand. What that means? Scale border effect, the modifier area, unit problem, or spatial autocorrelation? No one? Well, basically those are things that if you don't know what they are, you might be doing super wrong analysis with that. Scale, you know, we have a scale, right? That means that it's not the same thing if I look at my data or my reality that is in the data at small scale or a larger scale, right? And I don't know if I can paint somewhere. This is one thing that usually when we talk, thank you, when we talk about scale, you know, you've heard for sure about big data, right? This super trendy word now. Okay, so buzzword like big data, big data. Everyone loves big data. That means that you have data with an incredible resolution, like millions of data. And people tend to think that it's better to have more data. Like, I'm going to do some hydrological analysis. And I have a digital elevation model with a 30, 90 meters cell size. And then I have one that is like 1 meter, like super accurate. Yes, fantastic. It's like, that one's better. Not necessarily. Because it's a matter of scales. If you're analyzing a full watershed, you know, that process doesn't happen at that scale, right? And here's a small example. I can paint it. Not here, right? No, it's here. So what is that? Is that a valley or is the top of a hill? Depends on the scale, right? If I take this is the size that I'm analyzing, right? This is clearly the valley. But if I just take that part, I'm actually at the top of the hill, right? So the scale changes the results completely, right? If I'm analyzing, you know, if I'm like a human being and I want to analyze how this terrain is for me for walking, I should take this scale. But if I'm a little ant or something like that, I might take that one. This is like actually a hill for a small insect, but it's not for me. I mean, I wouldn't say this is a hill. For me, there's no problem to walk on that, right? So you always have to take into account the scale, right? And that's the first thing you have to do. When you get some data, think about the scale of the data. It might be very good, very accurate, but it might not be the data you need for your analysis, right? Important thing. Border effect. His turn. Okay, it's here. Leon, it's in here. No problem. Thank you. Anyone knows what that border effect is? No? You know, these things are pretty obvious, but some people might think. So you're here in a faculty of forestry. You study forestry here, right? So let's say I have my forest, right, with a lot of trees. And what I want to do is just find the density of those trees. It's easy. I just put a circle in here. I count the number of trees. I know the area of the circle, and I just do it. It's pretty easy. What if I put a circle in here? And this is a lake. You know, this seems pretty obvious, but some people don't think of it as like, okay, I count the number of trees and I get the area. But it's not true. You're in the border. You're being affected by being at the border, right? And that seems pretty obvious in this case, but there are other cases in which it's not that obvious, okay, that you are working on the border, so you have to take that into account. That's something with spatial data. Probably the one that you haven't heard about, although it's super important, it's the Modifier Area Unit problem. Anyone heard of that? Yeah? Okay. Well, for those of you that didn't hear about that, is sometimes we just use units, what we consider a unit, a spatial unit, that are not natural. Like, you know, you have, let's say, United States, right? And you want to make a map of the average income in the United States, and you just take the states, right? And you just divide a whole country by a criteria that is not natural. It's just a political reason, right? And each of these units, you just have your results. You know, the average income in this unit, right? But what if you do a different division? Your results are going to be different. So your results are affected by how you change your units, right? And that's something you always have to have into account when you are working with those kind of units, things that cannot be measured at a point, but you need a surface. Like you know, in here, like you need to take a surface to get the minimum, the average of something, right? And then the spatial autocorrelation. That's one of the cases of the Korean, actually, I mentioned before. If I'm here, let's say I'm here, and I say like the temperature here in the room is 20 degrees, right? And over there, it's 5 degrees, right? So 20 here, 5 in there. What do you think will be here, just 10 centimeters from me? Closer to 20 or closer to 5? Closer to 20, right? Things that are close are more similar, right? Well, that doesn't happen always. That's true. And that is one of the things that has to happen to interpolate data. Okay, if you're interpolating data, you need to know that there's a spatial autocorrelation. Things that are closer are more similar. But that doesn't happen always. There's negative spatial autocorrelation. Things that are closer sometimes are more different than things that are separated, right? And that's something that has to be taken into account when you work with the data. So this is some very, very simple ideas, 4 very simple ideas, but if you don't take them into account, you might be using a software like QGIS perfectly, you might be actually stating your problem correctly, but all you're doing might be completely useless, right? So when you work with spatial data, you have to know your data, right? You have to know what your data is about, right? Okay. Then there are some ideas that you have to know, you know, some basic things. You know, I told you that there are 500 algorithms in the software, or more in software like processing. But there's some basic fundamentals that you have to know to be able to browse through all of them. First of all is spatial statistics. How many people here have done some spatial statistics? Actually, well, quite a few, not every one of you, right? Okay, when you're going to do any kind of analysis with normal data, you at least need to know some basic statistics. You know, how to calculate the average, how to calculate standard deviation. Those are very simple and very important concepts. The same concept exists for spatial data, and you have to know them, right? This is pretty basic, but it's something that, you know, it's very useful, and ideas that are important. If we are working with raster layers, it's very good to have an idea about the so-called map algebra. There's a different operations that you can do on raster layers that basically they apply to this. They are defined to these 4 blocks. Local, this is you just get the value at a single cell, a single pixel. Focal, you get the value of the pixel and the ones surrounding it, right? So there's different kinds of, as I said, I'm not going to explain that all, but I just want to give you this idea so then you can just look for it. But it would be very good to have a different idea of this classification of operations, so then you can have it more clear when you're going to look for something, right? This is a typical thing. If you're working with vector layers, it would be good to have an idea of this geometric operation overlays, you know, having several layers with polygons and, you know, understand what it means to clip it one with the other, an intersection, union, etc. So those are operations that are currently, normally done on vector layers, and there's something that it's basic to have some knowledge. My favorite, although not everyone has it, is databases. How many people here knows a query language like SQL? 2, 3, okay, right. If you're going to work with a vector layer, you know the vector layer, I guess you know that, has some attributes. There's the geometry, right? And then there's a table with attributes. If you don't use this kind of languages, that query languages, you're basically wasting time, basically. Because there are things like finding this and that with a single line of a query language, you can get a lot of information. Like, I want to see all the data that had this and that and that. And, you know, it's super easy. It's not super easy, but it's very concise. Like with a couple of phrases, you get it, with a couple of sentences. But if not, that might take you ages, or you're not going never to get it, right? So query languages, if you're going to deal with that data, should be a must, right? Knowing some query languages, being able to actually query your data. It's like ask your data something. Yeah? You know, the idea is to solve a problem. We're asking questions to your data to get the answer to our problem, right? And the best thing when you're working with that is query languages. So those are my recommendations before, if you really want to get serious into spatial data analysis and do something that is correct and good, you should get a good understanding of this basic ideas, right? Once you have that, then you can start like searching for the correct algorithms, etc., right? So now imagine that you've passed through all that and you have a good understanding about spatial statistics, raster layers, vector layers, etc. Now you go to processing, you find an algorithm that, yeah, this algorithm is good. I mean, this is what I have to run this and this and this algorithm to do all my workflow and end up with my result. Okay, an important thing is doing that, understanding what you're doing, knowing what you're doing, right? And most of the people use algorithms wrong. My favorite example, as I said, is QGIS, right? But there are hundreds of algorithms that people misuse, right? What's the problem with QGIS? It's very complex. When I say very complex, I mean very complex, right? The mathematical ideas underneath that, they're complex, right? And then there are a lot of different cases, situations, there are different kinds of QGIS. It's complex, right? So if you want to use it, you want to learn it, you're not going to learn it with a couple of pages. No, you need a book. You need to read it, you need to study it, right? It's appealing, it's very cool. People love it. I don't know why, it's cool. You know, if you use some other kind of interpolation, it's not so cool. If you use QGIS, oh yeah, that's cool, that's trendy. Don't tell me why, but people love it, right? And you see a lot of people trying to, this is very common in like mailing lists, like, oh yeah, I don't want to use that interpolation method. Must be better if I use QGIS. Why? Why it's better? Tell me why it's better. I don't know, must be better. So, people like it. Don't tell me why. The results are nice. When you take a layer with points and you interpolate and you get a raster layer and you interpolate a raster layer, it looks very nice. You know, this is smooth. It's lovely. It doesn't mean that it's nice, but people like it. You know, QGIS. If you use some other interpolation method, you can see some artifacts and it's not that nice. So people tend to use QGIS because, you know, it looks very nice. It's visually very nice. It's easy to apply. That means that thanks to the software that we have for using QGIS, you can use QGIS if the only thing that you can do is click next, next, next. That's it. It's very easy to use, very easy to apply. So people think that, you know, it's easy. It cannot be bad. You know, I click, 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 and then I get a nice result. So it has to be like that, right? So as a consequence of that is frequently misused. Frequently, that means 90% of the time. So very frequently, right? And people still love QGIS. This is not QGIS. This is QGIS, spatial analyst. I don't know if you know anyone familiar with that. Well, basically the idea in here is that if you don't understand every single field in here, you shouldn't be using that. As simple as that, basically. But there's a lovely next button. And you just put your points, you don't understand what that is, but you know it looks pretty cool, right? So you connect, 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 and you get with that. Oh, super, awesome, right? That's what people do, you know, and that's not correct. If you don't understand what you're doing here, you know, you might have a semi-variogram that shows actually that your data doesn't have a spatial correlation, which means that you cannot use QGIS. I mean, most of the people don't know what a semi-variogram is. Like, you know, it's some cool thing. You know, it's calculated there. I click on next and it works, right? So this is the thing, this is a bad thing. I mean, it's good if you understand because it makes it easier for you. It's user-friendly, that people would say in terms of computers, but it's too user-friendly, right? So this, for me, is something that shouldn't be that way, right? This is, as I said, from the spatial analyst, statistical analyst in QGIS, but you can find examples of that in other software. This is my favorite one because it's like, it looks so complex, but it looks so great, and it has this next button, so it's like super cool, and at the same, ridiculously easy and ridiculously easy to misuse, actually, right? Okay, I give you a layer with points, right? And I tell you interpolate the layer, right? So, and I come up with 3 different results, right? Which one is best? Which one of this one you think is more correct? There's clearly one of them that is more correct. But which one do you think is better? Okay, raise your hand if you think this is the best one.
It's the last one. It looks nice. The last one looks nice.
The last one looks nice. So we agree this is the best one? No?
No. The one I say it looks nice, but the right one.
You think it's that one? Well, the thing is that actually this is no best one, because you didn't ask me what is the variable that I was interpolating. You didn't ask me, let's assume that this is elevation. Where is that? Where is that elevation? This is where I live. Then if you take that into account, right, this is the best one, right? But if you live in a different place, there might be that one. Okay. The thing is that most people, when they are attracted by the nice looking thing, they just go for this one, which is, not surprisingly, the creaking one, right? So people love that one. Hey, look at that, there are terraces. Like, there are no terraces where I live. That's not a good thing, but depends. Where I live, there are terraces, right? What about the other one, you know, that other one? Some people, this is done using an inverse distance in weighting interpolation. And you know, you can see all these holes and points. They're actually the locations of the points that I use. So you can clearly see the points in there, the original points. Most people think it's like, no, because it's too bumpy. Like, it's rough. Like, people tend to, you know, like, that one is smooth. But you know, the world is not smooth. Sorry for saying that, but you know, the world is like that. So it depends on what you're interpolating, depends, or you have to know more things than just the basic algorithm. The algorithm itself is not correct or incorrect. It's your data, it's your situation, it's your context. So there's more information that you need, right? To know about that. This is important, don't lose that, right? So I took those points. This is the same as the other one, but in 2 dimensions instead of 3. And I just used the Kriging algorithm, right, to calculate 3 different surfaces. So I took, right? But they look great. It's like you get that, oh, yes, I made a nice interpolation. This is way different. This is way different. They're not so different, but you know, they're incorrect, right? So you can take the algorithm, enter wrong values, and get wrong results, right? And the thing is that it's difficult to use the correct one. But that's the reason why you have to know that knowledge. You must know the algorithm. You must know what you're doing, right? If you don't know it, you're going to get a nice result. But it's nice doesn't mean it's good. It can be nice and absolutely useless, right? So just take that into account. I'm sure you've seen this. This is one of the dangers of using a GIS, actually. I'm sure you've seen this in some film that, you know, they get this picture of a car with the bad guy and say, oh yeah, just give it to our whatever IT department, and it's like whatever, and they came up with that. Okay, right? From that, they get it, and it's like, hey, you know, this is a film. It's not real, right? If you have a picture like that, there's no way you can get that. That only happens in films. And you're not an expert. You're not experts on working with image data, right? But that doesn't sound very realistic, right? Now you're experts on working on spatial data, you and many other, and people actually think that if you have a layer with 3 points, you can actually get that. People do that, and it's like, if you put this into a Kriging algorithm, you're going to get that. You might get that, but that doesn't mean it's correct. It means that your Kriging algorithm has calculated that. You know, it's not so easy in here to see if it's correct or not. In the image in there, I can say it's correct because I actually can read something, you know. But in here, how do I know if it's correct? Well, it's not so obvious, but then you have to look it in here. You just have 4 points. There's no way you can have that, right? Okay, there's actually a branch of science called information theory that basically says that things like that are impossible, okay? If I take this very complex terrain and I put it into just 4 points, there's no way I can go back, right? I need more points, right? And when you use a software like processing, sometimes you know that there are limitations. Some other people, sometimes they just forget there are limitations, you know? It's like, you get a layer like that, and this doesn't have enough resolution. But you can tell processing to create, instead of this raster layer with 30-meter cell size, have one with 30 micrometers. And it works. I mean, it's going to calculate a massive raster layer, but it's going to, you know, invent the data, it's going to come up with the data. Those are no realistic data, right? So don't forget that. Sometimes it's like, you know, people say like, oh, there's like, processing allows me to go from points to raster. And I'm fine, I can calculate, that's not true. Right? You can get a raster, but it's crap, I mean, it's rubbish. Okay, so now assume that you know your stuff, you've been able to execute your algorithm, and you know what you're doing, so you get some nice result, right? Now, the last step is to show it to someone, to present it, right? So what you have is data, you have output data, output special data, right? Anyone knows the difference between data and information? Which is pretty important, by the way. No one? Okay, I'll explain to you. What I have here is, that's not my birthday, but let's say that I ask someone like, when is your birthday? And this is like, your birthday is the 26th of July, right? So these 3 blocks are data, 3 different data, right? You know, different combinations of characters, numbers, etc. But they give you the same information, right? The information is when you interpret the data, right? I just read the data and I take some information, right? This is how I would write that in Spanish. Like in Spain, we put the day, then the month and the year. Like English people do like month, day, year. And this is the same thing, but written down actually in English. You can write that in any other language, right? So it's different data and same information. The idea is that when we use software like processing, we're generating data, right? But data per se, it's useless. We have to transmit information. That's what we have to. If I'm given that map or whatever I have created to someone, I have to give information. If I just give the data, there's nothing. There are numbers and letters, there's nothing. So the idea when you create something when you present your results, is to present them in a way that you transmit the most possible information, right? Not the data. Data is useless. Information, it's useful, right? Information leads to knowledge, and knowledge is the important thing here, right? So I give you a list of 2,000 million entries with that. One for every single person in China, name, sex, age. Well, you got a lot of data, massive data. Is that any information, actually? Not much. You can use, what can you know about China if you look at something like that? That's the data, right? That might be the output of your algorithm, right? The output of your process, you just get a list like that. And it's like, I present it. I'm passing that to someone. Boom, here's the list. Okay? 2,000 million entries. I'm passing a lot of data, but not a lot of information, right? Because if someone looks at that, it's not going to know a lot about the Chinese population, Chinese demography, or even the Chinese politics, right? I can do things in my data to turn them into information, right? I just take my data, it's like, I don't need to have a massive list of entries. I just put it in here, simple graphic, pretty cool. Women, men, population, much better, right? So I've done things to my data to turn them into information, right? But it can go even farther. It's like, I can just sum it at 2 phrases. This is real information. So taking from that massive amount of data, I can use that. You know, there are more men than women, especially in the younger groups, right? And that, you know, the structure of this pyramid, it's conditioned by, you know, the one-child policy in China, right? And you can actually see that when the government introduced the one-child policy, everything changed, right? So, you know, we can even explain the politics of the country just in 2 phrases, coming from that data that has like 2,000 million entries that says nothing. It gives you no information, okay? So what you have to try to do when we do something like what we are going to do today, doing some analysis, when you end up with a raster vector layer, don't think like, okay, I got my layer, I put it in a map and I pass it to someone. That's not what you have to do. You have to take your data and maybe that map is perfect. Just put some nice coloring, some nice symbols and do that. But maybe not. Maybe you can just take the data and calculate some single value with it, the average value, and that's what you have to pass someone, right? So don't think that the outputs of a software like processing are the final outputs that you have to work with, right? Don't do the typical thing, like, you know, you do a project and then you give to your client or whoever, and, you know, pile of maps, like 1,000 maps that are completely useless. Don't do that. Just try to give information, not just data. Don't waste paper or hard drive space in there, right? we're working on a spatial data, and spatial data equals map. That's what most people think. You know, spatial data means a map. That's not true. A map is not always the best way of transmitting the information, right? You can pass a map, but you can do other things. You can create a graph like the one that I show. You can just calculate numbers or even a phrase. Write it down, like what I did for the Chinese population. Like, you know, write things down in a single phrase or a number or a graph, whatever. Just try to display the data in a way that is more informative, right? And a map is not always the best one, right? So we love maps, but they're not the best thing, right? A map itself is something for spatial analysis. When someone gets a map, it's going to analyze it, actually. So your task when you create a map is make it more evident. So when someone sees the map, actually gets more information and it's able to do extra analysis, right? And one important thing that we're going to see is that you can use spatial analysis not to get a result, actually, but once you have the result, do more analysis to make it look better, more informative, right? Like adding water lines, hill shade, contour lines, those are things that come from the analysis, but you're not going to actually to use them as a result. Just you're going to use it to enhance the result. I'm going to show you an example of that, right? Anyone knows that map? Yeah? That's supposed to be one of the best maps ever done. It's a wonderful, fantastic piece of data display. Basically tells the story of how the French people went to Russia to fight, and then they came back, and you know, this is a graph showing the temperature, so you can see like the Russian coal actually was killing the troops, the Polish troops, when they went to Russia, right? This was done by a French guy, and it's actually, as I said, considered to be like a fantastic display of information. And this is what you have to try to do, not the typical map like, yeah, here are the French, here are the Russians, like, you know, try to do things. Of course you're not going to get to this level because this is, you know, absolutely amazing map. But the idea is to, you know, make your final data more informative. And in this case, it means combining this kind of map. It's not actually a map, but you know, yeah, it has some like geographical component with this showing the temperature, with some phrase in there that explains the idea. And by doing that, you clearly see why the French lost that battle against the Russians, right? And that's what you get. This is basically what the idea is, like try to do something like that. Something that actually gives information to the one that gets it. Like when you get it, you just see the information that you're going to transmit, right? Anyone knows that map? We're going to work with that map. Yeah, that's it. Okay, there's a guy called Jon Snow that, well, there was those places in here. There was a cholera outbreak in London, and they didn't know what was happening. People were dying of cholera. So they tried to find a reason, and no one could find a reason. And this guy called Jon Snow actually said, oh, I'm going to put in a map, you know, the number of deaths, and then the places where people took water. There were water sources in there. And it was pretty clear, by looking at that, we're going to do this with GIS actually later. It was pretty clear that most of the people were around one of the pumps, right? So it was like, you know, this pump in here, the water coming from the pump, it's not very healthy. People are dying from cholera, right? So this is the first time, and this is not so long ago, this is the first time that someone used the map for analysis. We're going to be here doing a lot of analysis with maps, and that might seem obvious to you, right? Like, you know, maps, analysis, they go well together. That's not true. That's actually not true until very recently. Like, if you see the history of cartography, we've been doing cartography since even before we were writing text. There were maps from many, many thousand years ago. But all the maps until very recently were maps that showed us what was in the terrain. Like there's a river in here, there's a sea, you know, maps just telling us the physical world, okay? And this thing about creating maps for analysis or maps that have some variables like, you know, like average income or the average age expectancy, things like that, you know, those are super recent. They're very, very recent. Like the history of cartography is a history of just telling what was in the terrain, right? The physical world. So this is pretty new. That's the idea that I want to tell you. We've been doing this kind of maps for not a long time. So it's not something that is natural or immediate to understand, right? In fact, when Jon Snow made that map, you know, for someone like you, and we are going to see when we do this exercise on GIS, it's obvious that there was a pump with a problem. When he said that, no one believed him. and people kept on dying, actually, right? So it's like, you have a map, what, you know? Most points of people dying are close to this pump, and what does that mean, right? So it was not so obvious for people at that time that a map could be used for analysis and for finding a solution to a problem. And what we are going to do in this course is just finding a solution to spatial problems using maps, right? So yeah, that's one of the things that I wanted to show. What's wrong with that graph? This is like, let's say that the voting intention. We have a right-wing party and a left-wing party, and this is the statistic. What's wrong with that graph?
The scale is wrong.
Scale is wrong. That's it, right? So what is wrong here? Is the data or the information? Information, right? The data is correct. 49%, 43. That's fine. That's correct. The numbers are correct. But then when you look at that information that it gives you, like, oh, the right-wing party is going to win by far, you know, like 3 times more votes than that. This is the kind of graph that you would see in a newspaper that supports the right-wing party, right? Okay. So it's like, this is done intentionally, right? But sometimes when you try to put your data on a map, or not in a map or in a graph, you can do this kind of things just by mistake. It's like, I have the data, let's put it into a graph or in a map. And you do it wrong. You're lying, actually. Yeah, you're lying with that because your data is correct, but the information that you put in there is not correct. Right? So if you actually want to lie, you can do that. There's a very good book called How to Lie with Maps that I actually recommend you. It's a very good one, actually. But sometimes you do that by mistake. Just like, let's make a map. And then you do a map, and you're having this kind of a mistake. So you just make sure that when you turn your data into information, you do it correctly. That's important. That's the reason why I wanted to show, you know, the difference between data and information. Right? Sometimes you do it like on purpose, right? This is like, as I said, if you want to have the right-wing party look more powerful, you put it like that. Also notice that by starting at 40%, all those small parties that might get 10% of the votes, they don't appear. So it's like, ooh, super cool. We have like 2 parties, no one else. Okay. Creating this map is not easy. How many people here has ever created a map? Everyone probably, right? Okay. How many of you have read a book about creating maps? No, almost not so much, right, actually. Okay, creating a map is not easy at all. It's a very difficult thing. So basically, those of you that created a map without reading a book about how to create a map, probably your map was pretty useless, I say. What's wrong with that map? What million things are wrong with that map? What's the wrongest thing that you can see in there, actually? Not the colors. The colors are horrible, but there's something worse than the colors.
Well, you could discuss the projection.
Yeah, that's it, the projection. That's very good. All the other people see that. It's a map that tell you, map or surveillance societies around the world. So you just get an idea of, the surface. Surface, it's important. Like, there's like Russia is super big in there, and it has this endemic surveillance society. You get an idea about how much space in the map is occupied by each one of the colors. But the thing is that it uses a Mercator projection. Mercator projection is very common. You are going to find it everywhere. And Mercator projection is very good for sailing. That's it. Right? And you use it everywhere, right? If you go to Google Maps, for instance, Google Maps uses it, I think it uses it. But when you see like the big map in Google Maps, you see things like, the size here is like the size of the full South America. It makes no sense. It's actually not the same surface. It's much, much, much smaller, right? But if you move in a Google map, it's easy to see. You have this scale bar, and you just, drag your map that way. The scale bar changes, actually, because the scale is not the same depending on where you are. As you go far from the equator, it changes, right? That's fine, because when you use Google Maps, not to see the whole map. Most of the time you just want to zoom and have a look at, the smaller terrain, and that's fine. Then it's not so much distortion. But when you're having a map like that, showing the full world, and the important aspect in it is the area, right? Then you have to take that into account. You cannot use a projection that gives the same area, in here to the United States, so twice the area to the United States, because it's false. It's not true, right? So Then the colors are terrible. There are colors in here that don't appear. There are colors in here that don't appear in the legend. There's like terrible map, but that's a normal map, normal that you can find in this website. It's a normal map. I've seen like maps like that plenty of time, and they're all very bad. If you want to know about very bad maps and learn about it, there's a very good blog called Catastrophe, and it's super cool. It's super fun to look at it, right? So you look on it on the internet, and there's a guy commenting on it, right? So creating a map is not easy. The most difficult thing about creating a map like that, this is called choropleth math, probably you've seen it. This is pretty recent. It's like 100 years ago, the first time that someone ever made a choropleth map. This is very typical now, but it's very recent actually. So one of the most difficult things is to select the colors. This is very difficult. And for most of people, like, okay, I just, get whatever color and automatic. You just click in your GIS, like, I have 7 classes. Okay, automatic color, 7 colors, and that's a guarantee of having a bad map, right? So imagine that this is a map. I haven't put any scale or any legend on it, but imagine that this is a map that has some kind of numeric variable, right? And this is pretty common. If you take a GIS, like, okay, I have values going from -10 to 10, let's say. Put a color ramp, and it puts a color ramp between purple and red. It's like, the thing is, the colors, you cannot order colors. You order them in a rainbow, but that's not the thing. You cannot order them. You can order the hue of the color. Like if you go from light yellow to dark yellow, yeah, that makes sense. Like you can order them. They're actually ordered. But colors themselves, you cannot put an order between yellow and blue. There's not. Like which one is higher, which one is, this is not a good idea. And a lot of people do that. You can see that in many different maps. Much better if you just actually, take from light brown to dark brown. You change the colors and you get much better. It's even better if I say, like, I go from -10 to 10, I get a negative value and a positive value. It would be good to just start on 0, 1 ramp for positive values, 1 ramp for negative values. So you can do it like that, right? It looks better, like, positive values for red, from light red to dark red, from light green to dark green. But then you forget that some people are colorblind, and they're going to see the same color. So it's quite tricky to come up with a nice palette of colors, right? There are a couple of books around there. One of the books, in case you want to see it, is by a colleague of mine that works at Boundless. It's called Gretchen Peterson, and it's called The Cartographer's Toolkit. It's a book about 2 things, basically, about how to select colors and do all that, and how to select fonts. Okay, you probably use labels, and that's not easy at all. Typography, selecting the right font, how to put it, it's everything but obvious. It's quite complicated, right? So it's an important thing to know about it. How many people have heard that phrase once? Every map. They told me that at the university. I don't know if the university here is better. But like every map must have a scale and a north arrow. It's like, you put people like failing exams just because they don't put an arrow or things like that, You agree with that, actually? Like most of the people automatically put a scale and a north arrow. It's like, I've seen north arrows in things like that. Where is the north arrow? This is the north. Like every direction goes north. This sounds ridiculous, but people put it in there. So you need a scale. This is a map of Spain with the results of the last elections. Like, why do you need a scale? Is someone going to measure? I mean, this is not a map for measure. It's a map to know, like, this party has won all over and the other one has won here. That's the thing. And then this map, if you say someone like, what's wrong with this map? It's like, oh yeah, it's missing the scale. Well, the wrong thing is that it uses the same color for 2 things, almost the same color. That's not a good legend, right? So don't have this, try to get away from all this fixed rules, like every map must have a scale and I have to use that. Concentrate on other things, right? Just having your data is correct, your projection is correct. That's very, very important, I think. Yeah?
Well, if you don't know Spain, then you couldn't guess it's Spain, actually.
Yeah.
The scale would maybe help you there.
Well, I mean, this is a map about the election. Hey, if you don't know Spain, why are you interested in seeing who won the election in Spain? That's an important thing.
If I don't know it's Spain, you don't have a title on it, for instance.
Yeah, it must be good to Spain. Or I mean, I think that this should be part of, let's say, an article in a newspaper saying the results of the elections in Spain.
But But I mean that scale does not always be used to measure something, also to tell you actually what it is. Because of the scale.
Well, but what would change, like if, I don't know how big is, let's say, Denmark. I don't know the exact area of Denmark, but if I'm checking the result before coming here, like let's check the result of the last election. What is the difference between knowing that it's that big or that big? If it's a massive country or a tiny country? I want to know, like, this is basically a right-wing country, like most people vote right-wing. You know, it's I think. It's not that it would be bad. I mean, you can add a one, but for some people, it's like, oh, it doesn't have a scale. You know, it must have a scale. In this case, it would be worse. I mean, if you actually add a north arrow in there, that would be bad. Like here, the good thing is to add this. I don't know how it's called in English. In Spanish, it's called canevas. You know, that's lines that actually point north. That's a better idea, right? So I told you that we can use analysis for making things look nicer, right? I do all my process. And at the end, I came up with that, right? This is my result, right? After the analysis. It looks good. I put a nice color ramp in there, right? I put it like that. I'm like, okay, now I can put this into my document. But the thing is that I can use more analysis, not to get more data, but to make it look better, okay? This is an elevation data, so I can use a hill shade model, and I get this, you know, with like a shadow. I can better see the relief. Then with that one, I can do some analysis, and convert that raster layer into a vector layer with control lines. Then I put them all, and it looks much better. It gives me the information of that elevation much better, right? So I have all the data that I need in here. I mean, all the final result, my elevation result is in there. But I can do extra things to make it look more informative, right? So that's one thing that we're going to see as well. So when you reach your final result, don't think that the analysis is over. You can go farther and get some more analysis done, right? Okay. This is my last slide, right? Now we're going to start with the software.